Recording on. Good evening once again. Nice to see you all. Today it will be me rather than Quetta. Let's have a look at what you got with the warm-up test. So let me renew the page. Can you see my screen? Could you let me know if you can see my screen? Okay. Looks like everything. Why can't I see the chat for some reason? Give me a second. Okay, now I can. It's because this was a full screen page. Okay, then. Okay, so let me share it once again. So, so here were the questions. I can see the pictures this way. Oh, no, I can. Which formula describes allocation of n non-distinguishable balls into k baskets? So we have k baskets and k baskets. They are different, and we have n balls. They are all unique. So if it was the binomial coefficient, we would be rather labeling. We would be just picking k balls out of n balls. So it's not that. If yeah, just and clearly option number 2 is also a binomial. It is no different than option number 1, and so option number 4 is this one. I hope you can see it. It's a decreasing sequence of. It's a product of decreasing sequence of numbers. It's basically the same as option number 2, but without k factorial in the denominator. That means that you are not considering you are not so basically here in the binomial coefficient we have k factorial because we don't mind in which order we've picked k balls out of n balls. Balls are unique. So we just say that we've picked k of them and we don't mind the order. That's why we divide by k factorial to account for this. But here, if we don't divide by k factorial, it means that we are picking k objects, but we care about the order in which we pick them. It means that if it was this formula, then it would just mean that those k balls that we've picked, we enumerated them. But this does not give us information into k baskets. So if there are n indistinguishable balls and we put them into k baskets, so it's I believe it is not this thing either. So the only thing that is left is option number 3. And if you think about it, it is a formula that, if you remember the stars and bars trick, the stars and bars analogy, it is exactly that. So option number 3 was the correct one. Can I see the responses? How do I? This is strange. They've changed the interface a little bit. Questions. What if I click responses? 6. Okay, 6 responses. Yeah, so mostly you got it mostly right. Sorry. Most of you got it right. Which sign is before the first term in the inclusion-exclusion formula? So this is basically the starting. The first step of the inclusion-exclusion formula is the sum of probabilities of individual events, right? So it's the inclusion-exclusion. It tells you the probability of the union of several events, and it starts from the sum of their individual probabilities. Then you subtract from it the pairwise intersections. So it starts with a positive part. So let me see. Question number. I don't like this interface, to be honest. Yeah, also most of you got it right. It is plus. What is true about probability function? Let me just name things that are true, because it will be difficult to see how many of you got what right. So its values are between 0 and 1. That is true, of course. For all events, we have this. This is not true because we have inclusion-exclusion formula. This only works. When does this thing hold? Who can tell?
Disjoint events. Yeah,
so if it would only hold if they were not intersecting. So this is not true. Probability of event of a complement to an event is 1 minus probability of the event. That is true. And probability of nothing is 0. I get it's. I guess it's. This is also technically true. It depends on what you mean by nothing. Basically, if we do probability in this axiomatic way, we have the sample space, right? So this formula says that if you pick an empty set as a subset of the sample space, then its probability is 0. Yeah, that is true, of course. Is it true that the conditional probability of B given A equals vice versa? Okay, and we have options. Of course, it is not always true, right? But let's see what other options. True if one of A and B is nothing. Yes, that is true, because if one of them is nothing, then to get but you would be dividing by yeah, I guess that would be you would be dividing by 0. So in the bias formula, let's see what else. So if A equals B, that is it a multiple choice? Yeah, it is a multiple choice. So it is certainly true if A equals B, because then they are the same, right? Right. It is it true if that this is also under this condition, it is also true, because from bias formula you can see that. I hope you've seen the lecture for this. Right. And about this one, so if one of them is everything, then the probability, so the one of them is the whole sample space. Then then the probability of that one event is just 1, and then you are basically saying P of A equals B equals P of B given A, and you should also multiply or divide by the other probability. So that is not true, and I believe that when one of them is nothing, this is the only one I'm concerned with. when one of them is nothing, you will be in trouble defining one of them. One of the probabilities. So, but probability of nothing given anything should be 0. And I believe they would maybe cancel out. So then you will have, yeah, I guess this could work. I'm sorry, I haven't thought too well about this. Name this for, so yeah, this is obviously bias rule. I'm sure most of you got it right. Let me now share my tablet screen. Yeah, if B is nothing, then yeah, P of B is of, so Evgeny is answering in the chat. He says that if B, for example, is nothing, then the probability of B is 0, as well as the probability of B given A. But how about probability of A given B? To find it, then it is just the probability of A, I guess, if you are given nothing. Nothing, if nothing happened, I would say that the probability of I would say that yeah, that's the point. If you have if you are dividing by P of nothing, you're in trouble because you are trying to divide by 0, but in the numerator of bias formula, you would then have P of something given nothing, and that thing, no, on the left you have P of nothing given P of something given nothing is P of nothing given something, which is 0, divided by P of nothing, which is also 0. And I'm thinking whether that leads you to say that anything conditioned by nothing, it is just it. Let me think. I think I'll be taking our time if I think too much about this. Let me share my screen and we'll have a look at the seminar problems. And let's discuss that in the chat if you want. So can you see my screen of the tablet? I'll be doing it in this way again. So I just need to do it this way. Okay, I'm sorry if the text is not too large here, but I'll try. I'll try my best so you can see it well. So I guess this way it is more or less readable, right? So we talked about how we define probability. Classically, we have the sample space, omega. It is a set where of all elementary events, an elementary event, it is an event that you cannot find smaller events in a sense, right? So it's the smallest event you can think of. And any other event is basically a collection of, or a subset of omega, and thus a collection of some elementary events. This notation is not entirely fair, but because this set of all elementary events, it may be uncountably large. But for now, we'll just think that it's just a normal set, okay? Yeah, you have, if you have a discrete probability, that is a set of some discrete set of equally likely outcomes. Then to define conditional probability, we need to be able to intersect two subsets of omega, and basically the probability of an event given some other event. This is just the definition, is the probability of their intersection. So it means that the probability that both events happened, because intersection corresponds to logical end of events, divided by the probability of the condition B happening, right? So this is not a symmetric formula, and in general, P of A given B is thus not equal to P of B given A, okay? So if if the sample space, the set of all elementary events is discrete, we can just say that probability is we have these vertical straight line brackets. They are basically just the cardinality of this set, okay? Okay, and here we have some problems to solve. This is all good. This is theory, but we'd like to solve some problems. So let's say we are rolling 2 dice. So each die is, of course, a cube. It has 6 sides, and we suppose that each side rolls out with equal probability. So the probability of any certain side as the result of the roll is 1/6. Find the probability that the first die result is less or equal to 3, right? So we have, you can say that we have we roll the die, and so out of all 6 possible outcomes, we have so die less than or equal than 3. It happens in 1, 2. If we roll out 1, 2, or 3 out of 4, 5, 6, right? Overall, so P of that being less than or equal to 3 equals 1/2. I guess that is that the first die is you were rolled. Sorry. I got it too straightforward. We roll the die. We roll it twice, and the sum of results is more than 6. Okay, and we should find the probability that the first die rolled something that is less than or equal than 3. So how do we do that? A good way is to draw the whole sample space, right? So die number 1 and die number 2, and you have 1, 1, 2, 3, 4, 5, 6, 2, 3, 4, 5, 6, right? And so and the so if we are and the level set of their sum is a straight line that looks something like this, right? So if you roll 2 and 2, their sum is oh, I guess I should have also you can't roll a 0, obviously, right? So their sum is either 1 or it is 2, or it is 3, which happens in these 3 cases where you have, I mean, something's wrong. It's because I started with 1, that's why. Okay. How do I do this? Give me a second. Sorry. 1, 2, 3, 4, 5, and so on. 1, 2, 3, and so on. And this is 0, and you cannot be there. What you can is if you are here, then the sum is 2. There are two. What's going on? Zoom is telling me I cannot share my screen. Now I'm sharing. Can you see it? I guess you can. So here we have sum being 2. Here we have sum being 4. 1 and no, not 2, but 1. So sum is here. Sum. I'm sorry. This is not my. Today is not my best day. 1, and you either get 1 and but you cannot roll a 0. You are actually only rolling. So the only points that are the true outcomes are here, right? So they are these points, right? So those that I have drawn on the axis, they never happen. And so you can either have I overcomplicate this, but anyway, so you can either have 2 being the overall sum, and there's 1 option for that. So you can have the total sum being so 2 and 1, or 1 and 2, that is 3, of course, and so on. And you know that with every step along this direction, the total sum increases by 1, basically. And you know that the sum of the results is more than 6. That happens when we have, so we have 4, 5, and finally we have 6, right? If we had 6 being the total, we were here, right? We started with 5 and 1, or we could have 4 and 2, or we could have 3 and 3, right? And so on. And so it was this line. And what's the probability that the first die is less than or equal to 3? So if we draw it, 2 and 5, and there we have 1 and 2 and 4, and 1 and 5. And we have how many points there? 5 here, I believe. Then you would have 4. 1, 2, 3, 4. Then you would have 3 and 2. I guess it's so 5 and 1, 4 and 2, 3 and 3, and so on. Yeah, that's correct. and then 6. Yeah, 6 and 1 would suffice. And that means that you have a point there. It is the diagonal of this. So it is so the probability that if you have the sum being more than equal 6 or more, it means that we have half of the square plus half that is including the diagonal. So there are how many? Yeah, so you can count them that way. 6 plus 5. Those are the number of points along the diagonals, and so on up to 1. And out of those, only those work for us where the first die is less than or equal than 3. So it is actually we are cutting this sub triangle. And if you count the number of points there, it would be 3 plus 2 plus 1. And there you go, 2 out of 7. Phew, sorry. I guess you got it. Okay, and yeah, now we are done with the dice. Let's have a look at more involved things. So if we want to define probability in a non-naive fashion, then we are dealing with this abstract theory that we have the sample space and we have a function on the sample space, and it measures the probability of an event, which is the subset of the sample space, right? Any event A is a subset of the sample space, and we assign probability to an event A. Give me a second. So we assign probability. Probability function is, it takes an event as an input and it assigns a number to the event, a number from 0 to 1. And what are other properties of this function? First of all, the probability of nothing is 0. The probability of the whole sample space is 1. And if we have a set of disjoint events, that means that they are pairwise not intersecting, right? Any pair of them does not intersect. It has an empty intersection. The probability of their union is the sum of the individual probabilities. And if they are not pairwise disjoint, then we have the inclusion-exclusion formula for that in general. And so the conditional probability is pretty much similar. With this, if we have this probability function, we want to define conditional probability, we take an event B, that is the condition. It has non-zero probability, some positive probability. Then if we have this probability function, we can define conditional probability as this ratio and so on. So you can say that you do the following. Basically, you had the whole sample space omega, and you had a subset B of it, right? So since B could be smaller than omega, but not an empty set, because its probability is positive. You can work with probabilities of events conditioned by B. So if you have some event A, you say that the probability of A given B is the the probability of A given B is the ratio of this area to the area of B, right? And B includes this intersection, right? So to the area of B, right? And that's why you, since B is smaller, you divide by P of B to renormalize probability, and you have that, right? And all the properties of probability hold for conditional probability. It is a number from 0 to 1, for an empty set it is 0. For the whole B is now B, the condition, becomes our sample space, the whole sample space, kind of. So its conditional probability is 1. And if you consider a set of disjoint, a collection of disjoint sets, then this formula holds, right? But also, in fact, inclusion-exclusion in general would hold for conditional probabilities. So we see that conditional probabilities are not very different from ordinary probabilities. Yeah, and also we have that if A is a subset of B, so it means if A is if we have the whole omega, we have B, we have A being the subset of B, then obviously if A is a subset of B, then P of A given B is greater or equal than the probability of A unconditioned by B, right? Because the area of A is the same, but it's, if we consider the ratio of A to the probability to the area of A to the area of B, this ratio is greater or equal than the ratio of area of A to the area of omega, right? It is all quite clear. And vice versa, if we have yeah, let's just write it for the same picture. We have that P of B given A would be just 1, because if we know that A happened as a condition, it means that for sure B happened. If we landed somewhere inside A, for sure we landed somewhere inside B, right? And you can also get it from the formula, not from drawing stuff. But drawing stuff helps you understand better, I guess. Okay. So probability of intersection of events. So we know that probability of the intersection of two events, it takes part in the definition of conditional probability, so we can rewrite it in two ways. it is sometimes this is called product rule of probability. So we have P of A given B times P of B. This is an even better formula to memorize than starting with the conditional probability. So you can open it up like this, but this left-hand side is symmetric with respect to A and B, right? The right-hand side is not. So you can do it in the other order, and you get that is P of B given A times P of A. And this equality is basically a bias rule, right? Because you can take P of B and take it to the denominator of the right-hand side, and you get a bias formula, right? So from that, you also can get that if you have an intersection of many events, such that probabilities of their intersections they are not zero, we have the following formula, that if you have probability of A1 intersecting with A2, so on, intersecting with AN, you can open it up in any order you want, but let's start from the first. So it is probability of A1 conditioned by the intersection of A2, A3, and so on, AN, times probability of, now you have A2 conditioned by A3 and so on up to AN, times and so on, times probability of next to last one n minus first given the last of them, times the probability of the last one. This is the last part of the formula, right? So you start, and like a ladder, you first have the first one conditioned by the intersection of all others, then the second conditioned by what's left, and so on. You can just get it from the formula. Is that clear? Can you give me a thumbs up? Some feedback, so I'm not alone. Okay, it seems like it's clear. Just trust me, you can get it from the formula, okay? Okay, and there is also a law of total probability. So if you have a set of events, even if it is not finite, but infinite, but countable, right? So you know that things can be countably infinite and uncountably infinite. If something is countably infinite, it means that if a set is countably infinite, it means that you can enumerate things in this set, and you will have natural numbers will be enough for enumerating things in this set. Okay, if it is uncountable, then you would need more than the infinite set of natural numbers to enumerate things in this set. So if you have a countable set of events, it means maybe infinite, but at least countable. Then what you have is the following, and their intersection is their intersection is their pairwise intersections are empty. So the way I prefer thinking about it is, again, in pictures, you have the whole, let's say you have the whole set sample space omega, you have it partitioned into sets B1, B2, and they are not intersecting. Okay, there's B3 and so on. Maybe infinitely many. Okay, then if you pick any event A inside of omega, then how do you find the probability of A? Probability of A is basically the area of this circle A, right? But you can find this by doing the following. So let's take this thing. It's the intersection, right? And since the B's are disjoint, they don't intersect, that means that the intersection of A with B2 does not intersect with the intersection of A and B3, right? So if B's partition the whole sample space, then they also the intersections with them also partition A, right? So how you can find the probability of A? You can just sum these areas of intersection of intersections of A with B's. So you can sum over B's the probabilities of intersections of A and B, certain B, and you can remember that that is basically the probability of A given a certain B times P of that B. Okay, and again, you can think about it in terms of reweighting the areas to get the probabilities, because conditional probability of A given B means that out of a certain B, I'm looking at this part, and the ratio of this area to the area of the whole that whole B is this conditional probability, right? So to find what area does that, what it is not the area but rather the ratio of areas. So to find the area, you need to multiply it by P of B, right? And that gives you the area of the intersection. I hope that was clear. Why do we care about this formula, you might ask? So yeah, so this is called a law of total probability. Probability, why do we care? So the short is LOTP. Why do we care? Because sometimes we can find such systems of events, such B's, that it is easy to find the probability of A given B and the probability of that B. Okay, and we will look at a problem where this can be useful. Okay, imagine you have a hat. It contains 100 coins, where 99 of them are fair, but one of the coins is double-headed. Okay, so you have coins, problem 2, coins with the heads or tails, heads or tails, and so on. There are 99 normal coins and one coin that has heads and heads. Okay, there is one such coin. So overall, 100 coins. A coin is chosen uniformly at random. So we choose a coin uniformly uniformly. And we flip it 7 times, and it lands heads all 7 times. Okay, so given this information, what is the probability of such an event? Okay, let's have a look at what events are handy to introduce here. So we can do the following. So yeah, but I guess it is so let's introduce an event B I. It means that it would be that we've chosen coin number I. Okay, so there will be 100 such events, and they should be pairwise disjoint, so they should not intersect. Is it true that such events don't intersect, right? I guess it is, because if we've chosen coin number I, then it means we have not chosen some other coin, right? So there is no outcome where where 2 different BIs happen, right? In our setting, right? There is no outcome that makes this possible. So obviously the probability of any certain coin being chosen is how much?
100.
Yeah, 1/100, and because we choose uniformly. And this is where the law of total probability, it helps us, right? So A is the event that we had 7 heads from 1 coin. So we took one certain coin, and we flipped it 7 times and got 7 heads, right? So clearly we now need to find 2 conditional probabilities: probability of A given B with the index being less than 100. Okay, so let's say that 100th coin, it was the fake one, right? So then what is the probability of that? So clearly if we took coin number, the last coin that only had heads and heads, so that was one head coin, right? And it would be just 1. Of course, if we flip such a coin 7 times, we would get 7 heads. But here we have what? How do we find this probability? So if we flip 1 time, we have heads with 1/2, right? And with 1/2, and if we yeah, so we should have it to power 7, of course, but so we make 7 do we need to account for the order of flips of tosses? This is exact. Yeah. So if it was I guess if we were flipping it 7 times, it was they were independent of each other, right? It means that it means that sorry, I have kids here. So yeah, so let's say we care about the order. So we flipped it once, then second time. So we were making a protocol, right? The first toss was either a head or a tail, right? Head, and so on. Head. We made 7 tosses. So the result of the if we mind the order, then of course there are 2 to power 7 possible outcomes, and out of them only 1 worked for us. That's why we have this 1/2 to power 7. So if we care about the order, then it is this way. Okay. And so we now use this law of total probability formula. Yeah, and you can see that so P of A was sum of over I of P of A given BI, P of BI. So for all of them that we have a sum over 99 first coins. There we had so we have 99 times probability of A given B with the index less than 100, P of B less than 100, plus P of A plus that last coin, where we have the conditional probability being 1, and the probability of that happening being 1 over 100. And here we also have 1 over 100. And the conditional probability there is 1 over 2 to power 7, right? So that should be the answer. 1 over 2 to power 7 times 99 over 100, so 0.99 plus 0.01. So the answer apparently is approximately 0.017. So a bit, just a tiny bit larger than 1 out of 100. So it should tell us that if you have 100 coins and only one of them is such a fake one, if you flipped it 7 times and you got 7 heads, it is not too much evidence that it was the fake coin. It could have quite likely happened because it was some other fair coin that just happened to drop head 7 times, right? There are but of course this probability would increase that. Not the probability, it's the probability of observing 7 heads, right? That it would of course decrease with the number of flips, and so it's almost as likely to see 7 head. Yeah, it's vice versa. It's almost as likely to see 7 heads as it is to just as likely it is that this it was the fake coin that we've picked, which happens with probability 100, right? 1/100. Okay. And also you have bias rule. We've seen the bias rule for two events, A and B. But we also can have a look at it if we have such a set of events that partitions. Let's say so. It's there are some things written there, some some statements about these events. But again, imagine you have a partitioning of the B1, B2, B3 of the whole sample space, and some event A, there. So what can we say? We said something about probability of A. That law of total probability tells us that probability of the whole A is the sum of products of conditional probabilities of A given certain B times the probability of that certain B. Now we can write it in the other way. We can say that probability of a certain B, let me write I, not K, I prefer I to be the index of certain B given A. Of course, it is by definition the probability of the intersection over P of A. But using bias rule, you can say that the probability of intersection is so you have the other order of in the conditional probability. So you have P of BI, and in the denominator you have P of A. And for that one, you use LOTP, which says that to find this P of A, we have a law of total probability, and so that equals the sum over now this time let it be J, P of A given PJ times P of PJ. So what's the punchline, right? What did I want to say in this statement? So the probability of a certain B given A is what? You have a fraction. In the denominator, you have a sum of all such things, P of A given a certain Bj times P of Bj. And in the numerator, you have only a certain term taken out of this summation. So it's a ratio of one term to the whole sum, right? So that one term is P of A given a certain B times P of that B, right? The ratio of one term to the whole sum. So here's the problem to illustrate this formula. Again, we have this 100 of coins, and the last of them is the fake one, double-headed. I guess this is problem number 3. Again, heads, tails, and so on. Heads, tails. There are 99 such coins, and the last coin is heads, heads. There is one such. A coin is chosen again. You uniformly choose a coin, and then you flip this coin 7 times and you see that probability. You see that it was you've seen 7 heads. Now you want probability that I was 100. Okay, so we've chosen again. BI is the event that we've chosen. We've chosen ETH coin, and we want to find the probability of B of I being equal to 100. So I can just write probability of B 100 given A that we've seen 7 heads, right? Can we find this if we have the result of the previous problem? We certainly have P of A, right? It should be helpful, right? So we can say that this is P of A given B100 times P of B100 divided by P of A, which from the previous problem, right? And B, the probability of choosing 100th coin is 1 over 100. And the probability that we see 7 heads, if we've chosen coin number 100, is of course just 1, because it is the fake coin. And so we just see that it is 1 over 100 times P of A. Let's see how much, and that P of A is just a tiny bit greater than 100th, right? It was just a tiny bit greater, so even without looking at the answer, we should say that it is not very small, this probability, right? So, and it turns out that it is 0.56, right? So I was wrong. Seeing 7 heads is enough evidence. So it is evidence to say that with probability 0.56, it was that last coin that gave us 7 heads, right? Sounds reasonable, even though it seems there are 100 coins, there are 99 normal coins. If you see 7 heads, it is enough evidence to say that it was that last one with probability larger than 1/2. Does that make sense so far? Can you give me some feedback? Oh, I see a question from Igor in the chat, but I believe it's too late, right? It was some time ago. Vladislav says everything is clear. Thank you. Oh, sorry, my tablet switched off. Let me ask it differently. Is there anyone who is lost or maybe has a question? Because now it's right time to ask a question, maybe. I can't hear any questions. So I guess we can just continue, right? Okay, this is an interesting and somewhat helpful problem to, not helpful, but educative problem. It's about smoking and its relation to cancer, unfortunately. But the data, I'm not. So I guess this data should be almost almost true. So you can make some conclusions from this. So according to some data from the United States, if a man is smoking, then it is 23 times more likely to develop lung cancer than if we don't smoke, right? If a person does not smoke, which is a huge number, right? So an order of the probability is an order of magnitude larger. It's a very big factor, right? So the lesson is don't smoke. It's bad for your health. And so let me say that I have event C, which is for cancer, and S would be smoking. Okay. So we know that P of C given S is 23 times P of C if we are not the complement of smoking, right? So we can also write not smoking, but in the lecture slides I have this notation complement for S, right? And also we know the following. We know that the probability of smoking, if we uniformly, if not uniformly, but if we randomly pick a person out from the crowd, then the probability that he or she, I guess this is data for men. If we pick a random man out of a crowd, the probability of smoking would be 21.6%. What is the probability in the US? A man is a smoker, given that he developed cancer, unfortunately. So you can see that this does not tell us the causal relationship between cancer and lung cancer and smoking, but at least it tells us what are the chances that the lung cancer that the person, that someone unfortunately had was due to smoking, right? So this is how we would interpret this probability. So what is the probability that the man was a smoker, given that he unfortunately got lung cancer? Of course, we can use a bias rule for that, right? So that is P of C given S times P of S. So P of S, we have it. Let me circle that. That we know. P of C given S, we don't know it exactly, but we know its ratio. How it relates to P of C given the complement of S, right? So we can write, we can divide by P of, so so from the bias rule, we should have P of C here. But we don't have that data. But we can rewrite this. So by law of total probability, it's P of C given S times P of S. It's what we have in the numerator, right? So it's exactly the numerator. Plus, so this is the same as the numerator. Plus P of C given the complement times P of the complement. Okay. So we can divide this whole fraction by both the numerator and the denominator by the numerator, and we would have 1 over 1 plus what? This thing. So P of C given S complement, P of S complement, and P of C given S, P of S. So we know that this ratio equals what? 1 over 23, right? So this is 1 over 23. And we know this, P of smoking, it is 21.6%. And we know that to find this, we need to subtract P of S from 1. So 1 minus 21.6 over 100. Okay, so it's approximately 0.8. And that is approximately 4 times larger than that. So it's this thing is approximately 4, right? So there we have 20. So approximately that whole thing is 4 over 20. It's closer to 24 than to 20, right? So it's approximately 1 over 6, right? So 1 plus 1 over 6, we have 1 over 1 plus 1 over 6, it is 7 over 6, so it is approximately 6 over 7. And that is quite a lot. It is 0.8, right? So the reason for, given this data, we see that the most likely explanation, at least the most likely, right? It is not the it is not necessarily a reason of lung cancer in each certain case, for each certain patient. Of course, conditional probability does not tell you the true relation, what is the cause and what is the effect. It only tells you the likelihood of that, right? So it tells you that it is quite likely that if a person unfortunately had lung cancer, it was quite likely that he was a smoker, right? So things are this way, given this statistics, given this data. Okay, so now we have the famous Monty Hall paradox in problem number 5. I guess some of you heard of the Monty Hall problem. It is a paradox, and the resolution of it is quite interesting. So could you raise a hand if you know this, if you've heard of this story? No one heard about. Okay, Evgeny says he heard about Monty Hall. So imagine you are on a TV show where you're playing a game. So you are asked to give me a second. I'll just reconnect the pencil. So it gives me proper lines. So you have three boxes kind of to choose from, okay? And behind two of them you have well, in the original show they have goats, not true goats, but not real goats, but images of goats. And behind one of them there is a car that you get as a prize if you pick the right door, okay? And the story is as follows. So this is what you have in theory, right? So and you have three doors: door number 1, door number 2, and door number 3. And let's say you picked a certain door. Obviously the order doesn't matter much. Let's say you picked door number 2, okay? Then the show host opens one of the he opens one of the remaining doors. Let's say door number 3. My tablet stopped streaming for some reason. Sorry, just a second. I can't see. I still can't see my screen. There we go. So where were we? Monty Hall. So let's say you picked door number 2. And since there are two goats, there are two doors behind which there is no prize. Obviously, even if you chose the door behind which there is no prize, there is at least there is one more that has no prize behind it, right? And Monty, the host of the show, he knows where the prize is. So even if you've chosen the wrong door, he opens another door and he says, okay, so there is no prize behind the third door, the one that you haven't chosen, right? And the question is, does that affect your choice? So he gives you an option to either change your choice after he revealed that door number 3 had no prize behind it, or to stay with your choice and keep saying that you prefer door number 2, and yeah, so that's the point. And apparently it is a paradox, because it is not it is not very obvious because from some common sense, it seems that there were two doors with no prizes, two doors with goats, and you've chosen a certain door. He opened another door. He always opens the door with no prize behind it, right? So it kind of so your chance of winning it increased now, but the point is that it seems that the chances of winning for this second door should still be the same as the chance of winning if you change your decision, right, and pick the first door. So it seems at first that there is no reason to switch. Okay, so let's try resolving this paradox. Let's find the probability. So here's the a proposition of how we could solve this. Okay, so let's introduce the following events. So let's find that the probability if we don't switch our choice. Okay. So the let's say we again nothing here depends on the order of doors. Nothing here depends on the numbers that we assign to doors. So let's say we originally picked door number so it was another way around. So let's say we did it this way. So you first you picked this door. Then Monty opened this door number two, and there was a goat behind it. And there's this third door here, right? And the event, we have event CK. It means that car is behind cave. That's why I prefer I as an index, right? So car is behind door number I, if door. Okay. So what we are interested in is and the probability of Monty opening a certain door is, so MI is the fact that Monty opened if door. So here clearly Monty. So for this one, I is either well, actually I can only be two here, right? We decided that he would always be opening door number two. Then what we have is that the probability of what we're interested in is the probability of car being behind door number one, given that Monty opened the second door. So that is the probability of Monty opening the second door, given that car was behind the first one, right? Times the probability of car being behind the first door, which is independently of Monty choosing, right? You see, that's how Bayes formula helps us. This probability does not depend on Monty. It is just 1/3 clearly, right? If we shuffle everything fairly. So the probability of M2, so the probability that Monty would open door number 2, so this solution says that it is 1/2 actually, but I'm not sure that is correct. But let's say because so the reasoning is that if it is not if it is independent of the car, then Monty has two doors to choose from, and he so the assumption here is that he uniformly picks. He is not interested at not letting you win, okay, which is not very realistic, but if once you've chosen, once you've said that you want to open the first door, that's why we labeled that door to be the first. Once you've opened that first door, there are 2 doors left, and he just randomly opens one of them. But there's a problem with that, because in Monty Hall he always opens a door where there is a goat, right? So I actually disagree with this part of the solution, to be honest. But anyway, and then this conditional probability is that Monty opens door number 2 if you've chosen the first door, and I guess this probability is also 1/2 in this solution, and so the solution tells you that it is 1/3, which is smaller than 1/2, because it seems that if you change your choice, there are 2 doors left, and if you change your choice, the chance of winning would be 1/2, which is larger than 1/3. Yeah. But to be honest, this is not an end. So we have this solution written from last year, but when I started thinking about it, I thought I do not entirely agree with this, because here's that there's a proper solution. I know it exists. It was proposed by Marilyn Vos Savant, and it is indisputably correct. I will send it to you. I will send it to you in the chat. For now, let's let me leave this for you to digest. So the Monty Hall problem is a very
yes, I'm sorry. Yes, it's a very famous paradox. But I want to ask you, could you tell us what's the difference between calculus if the person change the door one step and don't change the door? What's the difference between how to calculate this probability? I don't understand. I also think about this paradox, and I don't understand it, how it's possible.
Yeah, it's a complicated thing. Yeah, surely. So Evgeny sent a link to the Monty Hall problem on Wikipedia. Of course, yeah, of course, it has a Wikipedia page dedicated to it. So to be honest, I don't agree. I don't remember the proper solution by Marilyn Vos Savant or whoever that was. So I can't even tell you if this is the right answer, because you see, so we have this conditional probability of Monty opening the second door, given that you've chosen the first one, but it seems that it is so. This 1/2 is not. It is a very strange thing, because I would say that this probability is 1, because we labeled the doors this way. Because you see, the second line of the bullet list, it says the door that Monty opens is door number 2. So Monty always opens door number 2, no matter what was the condition, right? So that's why I think this solution is not exactly correct. And that's and also so. But I'm not sure about this one, that probability of Monty opening door number 2. Of course, we can say that it is probability of Monty opening door number 2, given that you've opened door number 1 times the probability you've opened door number 1 plus the probability of Monty opening door number 2, given that you were not opening door number 1 times the probability of that. But the fact is that that this is 0. You're always then it's then this is 1, and so I would say that. But then this is so that we have a trouble here. We are conditioning by an empty set. This never happens. You always open door number 1. So then it would be just P of M, and you would just have this leads you to this 1/3. Even if this probability is not 1/2, there's this question left. The problem is that this solution labels the doors in this way, as Monty is always opening door number 2. I invite you to think on this, okay? For this week until our next class, okay? Maybe you'd like to think a bit on your own, but be informed that a final proper solution actually exists, and maybe I will just leave you the pleasure to think about this for a couple of days, and I will then send you the or I can send you the proper solution, and if you want to think about it on your own, don't read it. Think about it on your own. Okay, shall we do it this way then? So this is kind of, we are leaving this as an open kind of question for ourselves. But overall today we solved several problems on conditional probability, and so we know we now know many things about it, that there is the law of total probability even for conditional probabilities and all that. So yeah, and the bias rule, of course. Are there any other questions, maybe? Or was that clear?
Max, can I ask you please one question? My last question. So can I understand? Did I understand correctly that contestant from the last paradox or picks one door, and after that Monty open not this door but one of the others. Yes, and after that he told some words about some changing. Yes, you need to change or you not to change.
After that, he proposes you to either change your choice to another unopened door, or keep your choice and open that door that you've chosen at first.
Okay, thank you.
Yeah. Okay, then if there are no other questions, you can always ask questions in the chat. You can also always write me directly if you have some other question, or to Kola. We don't mind at any time. So please. Let's keep in touch, and I guess then it will be it for today. There will be the recording. So I guess I'll just stop the call, and have a nice evening, everyone. See you soon. Let's keep in touch in the chat. Thank you for being with me here today.